Okay, so in this video we're going to introduce combination logic. So we're going to be using our logic gates to build combination circuits. So we're going to be using multiple gates in each circuit. And what we're going to look at today is just focus in on the diagrams and the Boolean expressions. Okay, so being able to write out the Boolean expression from the combination circuit, and also be able to draw a circuit from the combination expression. Alright, so first thing we need to do is just remember our Boolean expressions and how they work. So the not is just a letter with a single letter with a line over it. And is multiplication, or is addition. NAND is multiplication not, and NOR is addition not. Okay, so we're not going to be incorporating the exclusive gates with any of this. So first we're going to look at writing the expression from the circuit. So basically we're just going to look at each gate one at a time and write the Boolean expression for each gate, combining them as we go to get to the final output expression. So we're just going to basically work across left to right from the input side till we get to the final output. Okay, and the expression will get longer as we move across. So that's how we're going to approach this. So here's a few examples that we'll go through to show you how to do that. Alright, so again, just need to remember the symbols and what gates they are associated with, then remember the Boolean expressions, and then pay attention to the lines as to where they are connected. So in the first one I have an and an or. So I want to start with the and. So I have A and B going to an and, so that is just A times B. Okay, and then that output of the and is going to the input of an or with B. So switch B is coming around and going into this or. So my final output expression here will be AB plus C. Okay, so that's the combination Boolean expression for that circuit, because here A and B are ANDed, then it goes into an OR, so we add it with B, not C. There is no C in this one. AB plus B for that example. Alright, so let's look at the next one. So I have A and B going into an OR, so that is A plus B. I have C and D going into an AND, so that is C times D. And then I have the output of these two gates going into an OR. So that just means I add these two together. So I have X equals A plus B plus CD. Alright, so here we have two addition operations. So to clearly indicate what is going on in this circuit, I'll want to put the A plus B in parentheses to indicate that that goes together with one OR, and then the second OR takes place once the C and D come in to the expression. Okay, so you want to use those parentheses to kind of designate where the logic gates are in the expression so that you know what is happening. Alright, so here I've got a NAND, two NANDs, an OR, and an inverter. So again, work our way left to right. So B is inverted, so that's B not. Then I have this going into an AND with A, so that'll be A times B not not. And then here I have B not going into a NAND with C, so that will be B not C not. And then those two NANDs are going into an OR, so that will be A, B not not plus B naught, C naught. Okay? So pay attention to the lines here. Okay, so that clearly indicates what is happening. So here I have just a short line over the B because the B is being inverted. The long line over the expression means the invert is taking place after the operation. So that's what these two circles here are for, these long lines. Okay, so you just pay attention to the invert that is taking place, whether it's happening on the input side or the output of the logical operation. Alright, so one other example here, I have A and B going into an OR, so that's going to be A plus B. I have B going into a NOR with C, so that'll be B plus C naught. I have these two gates going into a NAND, so that will be A plus B times B plus C naught, and then not the whole thing. And then I have this going into another NAND that is tied together on the input side. Okay, and anytime you have that with a NAND or a NOR, that basically just creates an inverter. Okay, and we'll do a little more in-depth study with this a little later on about NAND and NOR functions and things we can do with it. But just know that with a NAND and NOR, if the inputs are tied together, that basically makes it an inverter. So the output expression here will be A plus B times B plus C naught, not, and not again. Okay, so it's just one more line because this basically inverts whatever the signal that's coming out of this NAND right here. Alright, so that's how we write the expressions from the circuits. Alright, so next we're going to look at doing the opposite and drawing the circuit from the expression. Alright, so we want to look at the individual operations and then how they combine. So you kind of have to dissect these a little bit to see what's going on with each one of these. Alright, so in this first one I have Q equals AB plus C naught D. So A and B go together and C naught D go together, and then the two combine with this addition operation. Alright, so I'll start with the AB. So I have signal A and B, and that's going into a NAND. I'm having to draw on an angle here, so it's a little bit challenging. Alright, and then I have C naught D. So I have C, which is going to go to an inverter, and D, and that's going to go to an AND because it's multiplied, and then the two are going to go to an OR because they are added together. Okay, so that's my combination circuit for output Q. Alright, so the next one I have R equals AB plus BC naught. So I have A times B again, so that's another AND function. And then I have BC naught, so I'm going to jump off of B here because that's the same signal, and C, and that's going to go to a NAND because I have the long line over the operation, so that means the invert takes place after the operation. So again, you got to pay attention to the length of the lines to determine whether it's just a single input being inverted or the output being inverted. So the two are added together, so again that's going to be going to the OR gate, and that will be my output R. Alright, so this one here I have A naught times B naught plus C plus D. All right, so I have A and B is going to be inverted. So A inverted, B inverted, and that's going to go into an AND. All right, and then I have C and D, which I should have put these in parentheses. So C and D are going to be going to an OR together, and then the two gates there are going to come out and go into the last OR function to take care of this addition for output S. Okay, so this could have been, without the parentheses, it could have been just one OR function, so that AND plus C plus D. So that really does determine what gates are used in that. So that's why those are kind of important to have. So here we have T. So we have A times B naught. So that is a NAND gate. And then that is added to B. So I'm going to jump off of B here and go to an OR. And then all of that is added to C. So I'm going to bring switch C in, and that's going to go into another OR for output T. All right, and then one last example here for output U. So I got several invert functions going on here. So again, you just want to kind of pick this apart. So I have A naught plus B naught times C naught plus C plus D naught, and then that is added to this side with a naught over that. So a whole lot of knots here. So let's break this down. So we have switch A naught, so it's going to be inverted. It's going to combine with B by addition, so that is an OR function. But I have a line that goes over that OR function, so that actually makes it a NOR. Then it's going to combine with C by multiplication, so that is an AND. So C comes in and ANDs, but it's not an AND, it's actually a NAND because I have a line that goes over that operation to make it a NAND gate. Alright, and then I can come down here and combine C and D. So C and switch D are going to come together and go to a NOR. So I'm adding, and it's inverted. So that's a NOR. And then these two are going to come together to what? They're added together right here, and there's a line that goes across the entire expression, so that makes it a NOR for output U. Okay, so that's how we draw the combination circuits from the Boolean expressions. Okay, and I apologize for not drawing these neater. I would like you to draw them neat using your electronics template, but I don't have one here at home, so I'm not able to do that. But please get one of those templates so you can draw these neater with the symbols here, so hopefully you can understand my drawings here to get the gist of what's going on. Okay, so that's our introduction to combination logic, of being able to write the expression from the circuit and then being able to draw the circuit from the expression. So in the next video we'll incorporate the truth tables with our combination circuits. So I hope this helps you understand how to do this, and if you have any questions, let me know. Have a good day. Thank you.